Good morning again. Sorry, my system was kind of overloaded. So I've been editing some video. Okay, now I stop that process. Okay, let's start this lab. Okay, now we are at our Linux machine. So you go to your Canvas page, you download the files. So one of the files are your program file that you need to complete this lab, and the other one is the document that describes the lab. So let's take a look at the description of the lab and see what you need to do. Okay, so let's share that document. Okay, here is your module 3 lab. So activity 3.1, in activity 3.1, you need to install 4 library in your machine. So after you download this one and the program on your current directory on your Linux machine, if you are using your own personal computer, you need to install this library. If you are using the virtual lab machine, these library have been already installed for you and you are ready to go. So now let's switch back to the Linux machine and see how we can do this. All right, right now you will see my screen in here, my Linux machine. Let me clear the screen. So if you can see here, I have this module 3 lab.x where I have created this module lab3.txt. So as you know, .x is not readable in Linux environments in terminal. So that's the reason I converted to this file. So how do we do that? So let me remove the file, remove this txt and repeat the process for you. There is a tool in Linux called .x to txt. Basically convert whatever file you have in doc or docx to txt file. So if I gave the module 3.txt docx extension and I hit enter, it's gonna produce for me this file. So if you don't have this tool on your machine, you can use sudo apt install.x to txt, and Linux is going to install that tool for you. All right, now that we have a readable file in our Linux environment, then we can take a look at it and then copy and paste those commands directly to our Linux terminal. If you don't want to use this technique, you can simply open your docx document on Linux using lib software, and then copy from there and paste it in the terminal. So now that I have this file, I'll use less command to read those library and install them by one. So I have already installed this one. Let me try the second one. So this is the command, we just copy it. We exit from this by typing Q. We paste it and we hit enter. So we say yes, we want to continue, and Linux is going to install that library for us. Okay, we go to the other one. So these two libraries your system might already have, you might not need them, but to make sure, let's run them, install them. If in case we get error, that's fine, because the first two libraries should be enough for us. So as you can see here, it says that this package is not, was automatically installed and is no longer required. So let me try the other one, see if we need the other library. So let's module txt. Let's try this one. Copy Q to get out from that environment, and then paste. Okay, now we are installing this library. Okay. Let me. Go back. Okay, so we are done with that. So we installed the libraries and everything is ready for us for the next activity. Let's take a look at the next activity. Okay. So we install these 32-bit libraries, and now we move on to the next activity. Okay, in here, so you have two files in your lab 3 programs. One is file2.asm and the other one is file1.asm. Sorry, there is a typo here. This one is file2.asm. So open these two files using the Vim editor or any other editor that you like to use in the Linux environment. You can use Nano if you want. And find out the architecture from the code. Was it written for 32-bit machine or 64-bit processor? And why? So look at the register name. That's the hints. If you have listened or watched the video lecture, the lecture slide and the textbook, you know how to recognize assembly code for 64-bit machine and 32-bit machine. So if you go to your Linux environment and then let's go back to Linux. Here we are. So, all right, we go to Lab 3 program, and then we list the programs. As you can see here, we have file1.asm and file2.asm. We take a look at the content of this file. Since the files are small, we can use cat command to just check them, right? So file 1, as you can see, we have register AAX, EBX, ECX, and EDX, right? And you guys know that these registers are, anyone has answer, are they 32-bit or 64-bit?
32-bit.
That's correct, exactly. Okay, good. So we know this. Now let's check the other one. If you don't know the bit length of the register, you probably need to go back and take a look at the lecture material. Let's take a look at the second one. Cat file2.asm. Now you see that The register are starting with letter R, RAX, RDI, RSI, and RDX. So these registers start with R, and they are belong to, if they're not 32-bit, they are 64-bit processor. So that's an answer for this one. So these are basically the Hello World program. I posted a video regarding Hello Worlds, and I explained that there are two strategies to run it. One, you can use the Linux system call by programming register A, B, C, and D. And so once you program this register, you put your hello world message in the library using this command. Therefore, when you configure this register in using assembly using this command, then after you call the interrupt, then the system is going to read the configuration of those registers, and after it sees that it's a write command, it's gonna go to the part of the memory that you have put the message in there and print it out for you. So this is one of the way that you can basically print out something on the screen. The other strategy that I explained in that video was about using the macros. So we have print macro and read macro and some other useful macro that you can take from those libraries and use it. If you remember that those strategies are enabled by using these files. So asm_io.asm, cdl, asm-inc, and driver.c, and lastly, myprogram.asm. So if you have followed that lecture, you know how these files work. These files are enabling your macro. So if you want to use macro for print out and read function, then you need to have this file and you need to compile this file and get the object file and then link them together to obtain the binary file. Please listen to those video lecture. Otherwise, you are not able to move. So that's as simple as that. So go to that lecture materials and make sure that you watch the video, all of them, to be able to do this lab. Okay, let's go back to the lab again and see what else you need to do. Let's share it again. All right, so we answered question activity 3.2, part A. So in your lab report, you just organize your report based on the activities. If in one activity they ask you to run the code and you are required to show your output, you take a screenshot and put it under that activity. Okay, next one said assemble link and run assembly file.asm using the syntax below. So you have your ASM file, right? And that is written for 64-bit machine, and this is the command for it. So you just use NASM to get the object file. The object file is going to be file.o. So then you link it to get the binary file. You get the binary file, and then you simply run it. And what is the output of your executable on the screen? So let's see that. Again, we can use your lab. Okay, we are in a different directory, so we need to go back and cats or less our module to just copy and paste the command. So since you are not very advanced for now, so you just go here and
Professor, we can't see.
Oh, okay. Let me switch back to this Linux environment. Go back to Linux. Okay, right now we are reading the content of the lab description, right? In the lab description, we read that, okay, you want to basically create the object file for your file, 64-bit file, right? And this is the activity 3.2, right? So now we are reading it in Linux. And we said that just copy this one to get the object file and link the object file and run it. That's as simple as that. So you do this, just copy this, say Q, and then you need to be in the same directory as your program, otherwise it's going to get error. So we go to where the program is. You simply paste it. NASM is not installed in this machine. It's going to get error. So it says NASM not found, but can be installed with this command. So it tells you, okay, I don't have that, but if you want it, you can install it. I say, okay, so let's install it. But please don't give me any error. Okay, again, if you are using the virtual lab, this NASM is installed for you. But even if it's not installed, installation is easy. Just sudo apt install NASM. Done, and we're done, right? So now we go back to our command and see this time if it works. Oh, so again, we are installing the previous command. So we're gonna create the object file from the assembly file. You know that's a process, right? So once you create the object file, then you link it with libraries, and then you get the binary file. So let's see here. We run that command, and now we have file 2.0. Okay, now you're gonna see what you need to do next. Then you need simply to use LD command. If you don't know how to do it, you come back to the lab description and take a second look. So txt, just a simple LD command. So let's see that. So as you can see, you type ld file.o to create the a.out. That's the binary file for you. So ld, what was my file name? File2.o. Now enter. So if I say that, then if I take list, this time I'm gonna be seeing a.out. This is my executable. This is the file that I got from my assembly, and it is now ready to be run. To run it, what do? We just say ./a.out if the file is at the current directory. But if it's not at the current directory, you need to give a path to your file. So make sure that you are in the same directory, otherwise you get error. Now you can see that hello world is printed out in here. Just you follow instruction, it's going to be as easy as this. But as you do this, try to have some of those functions in your mind. I mean, some of those commands in your mind. So next time that you want to do it, you do it much easier. Let's switch back again. We go to the document. Okay, what do we need to do now? Okay, it asks you, okay, what is the executable? What is the output of your executable? This is a.out is your executable. So what is the output of it? Hello world. So you need to answer this question. And then what else you need to do? You need to take a screenshot of it and put it in here. Okay, this is easy. All right, so let's move on. Try to compile the same file 2.asm and generate a 32-bit object file. What Linux syntax would you use? And what is the result of your compile? And what are the conclusions you draw from this one? Okay, so this is very important, this question, okay? So you have a file, this is file 2.0, that it was written, I guess, for 32-bit processor, right? So this time it says that, okay, run this one. Let me check the file if it is for 32-bit or 64-bit. Let me check it quickly. Let's see. Cat file 2.s. Okay, so the register are starting with letter R. Therefore, the code is written for 64-bit machine. Now, the question asks you, can you produce a code that runs on 32-bit machine from this file? And this has been explained for you, I guess, in lecture 3 video. So it's regarding the compatibility. So when you write a code for 32-bit machine, can you run it on 64-bit machine? And the other side of the question is, if you write a code for 64-bit machine, can you run it on 32-bit machine? So as we explained at the beginning of this course, we said that writing assembly code is different from high-level languages. In high-level languages, you write your code, and then you don't care about the hardware platform. So you just write it, and then you write your Java. You're gonna go and run it everywhere with any computer, hardware. You don't ask your client, okay, is your machine is CPU is that or this, or is it like Intel? Is it like ARM architecture? You don't ask those questions. Just say, okay, this is my code, and you go and you run it. But for assembly, you ask those type of questions. Is your machine 32-bit machine? Is it ARM processor? Is it x86 architecture? Because all of these different machines require different coding, and they have different register name and different hardware. So going back to here, we are working on x86 architecture, but we have two types of it in this course, 32-bit and 64-bit. So when you write the program for 64-bit machine, means that registers are longer, right? 32-bit machine is half of it. So if you write something for 64-bit machine and you want to run it on 32-bit machine, think if it's possible or not. Probably not, because it asks for RAX register is a 64-bit register and you don't have it. How about the reverse? If you write something for a 32-bit machine, can you put it on a 64-bit machine? Can you put something small in something big? If you have a big box, right? Can you put a small box in it? The answer is yes. But if you have a big box, can you put it in a box that is half a size? The answer is no. You can't do that. Don't do it. Not good. All right. So find the assembly, the command that can generate a 32-bit object file and run it. See if it's run on this file. Next question, assemble link and run this one. This time you have a file 1.s, and this is written for 32-bit machine. So it asks you to do the same process, but you know that when you want to create the object file for 64-bit machine, the syntax is different. This is the syntax, and the syntax for the 32-bit machine is this one. So don't mix this up. So here, use this syntax to generate 32 bits. Object file, their object file name gonna be file 1.0. And then once you create the object file, as explained in the video lecture 3, then you need to link them together to create a binary file executable. So what is the command for 32-bit machine? This is my command, ld -m elf _ I 386. So you need these keywords. If you don't put this keyword, you're gonna get error. If you use like wrong keyword there, wrong options, you get error. You need to follow the instruction. You need to pay attention to detail. Somehow, if you memorize this, that is going to be great. Running the executable is the same. Just follow that process. Great. You have another question in here. What kind of object file was produced? 32-bit object file or 64-bit object? Can you generate 64-bit object file from file.asm? Try to see if you can produce a 64-bit object file from that file. The code is written for 32-bit machine, but you want to run it on 64-bit machine. Therefore, you have to create an object file for 64-bit machine. What's the command to do that? The command is given up in here. So just run this command for it. So say nazem elf on file1.asm. So once you do this, it's going to create object file for from your 32-bit machine, but the object file created is going to be 64-bit. Create your object file, then you use the linker LD, and then you run the command. And you will see that the 32-bit code is going to be run on your 64-bit machine. That's the conclusion. 32-bit can be run on 64-bit machine, but reverse not possible. Good. We learned something today. Now activity 3T, the 3-3. All right. In activity 3-3, we are reproducing the things that we have been talking about in lecture 3 video. So in lecture 3 video, you just watch, and watch. But now we are going to repeat the process in here to get familiar with it. How do we do it by ourselves? All the time instructor talking, and never, run anything. So let's do this in this lab. You run this file. Instruction is given. Just follow the instruction and see whether you are able to do this. This is one command. This one is only one command, okay? One single command. It's not 1, 2, 3, 4, 5, 6. It's not 6 commands. It's only one command. You copy it and paste it there, and basically you create the linker from it. So the first step, so you have 2 C file. This file is supposed to compute the factorial function for you. And then let's take a look at this file first. Let's take a look at this one. Okay, you're out. All right. Here. Let's see, what do we have? Okay, we wanted to see what is in test. Let's see. Oh, this is it. There's a main function. There is a prototyping for my function at the beginning of this file. Then I have x defined as 4. And we said printf what? Printf this, x factorial equal to d. What's the value of d? Oh, is fact x. Or where I can find fact x. Where is it? What is it? Oh, fact x. The function prototype is in here. It means that somewhere this function has been defined. So where is that somewhere? Is it in the same file? No, it's not in the same file. It's not in here. So where can I find it? Where is it? Let's search for it. Is it any fact function in here? Oh, we can see another C file. Oh, that's it. So let's take a look at it. So what's that function? Huh? Oh, it's defined in here. So integer fact, integer n, right? So it takes one integer and it's defined an output. If the integer is 0, the output is going to be 1. So 0 factorial is 1. Else, recursively generate the factorial for me and then return the output of that factorial. Once it returns, it goes back to the printf function, into the test file where we call it in here. So it compute the factorial of x, then it get the result back in here, and then print function is going to print out that file for us immediately. So in here, we learned that if we have multiple C file, how we can link them together. Basically, you are going to generate object file for each of them, right? As explained in your lab material, just use GCC and minus C option. Don't forget that. If you use GCC, right, and say test.c, this is not good. You know, the program is complaining. Why it's complaining? It says that no such file or library.
Hey,
correct.
Professor.
Yeah.
Something's up with your mic.
Oh, really?
Yeah.
How about now? Is it good?
No, it's the same problem. It sounds kind of like staticky.
Okay.
Yeah.
So let's see. If I use if I use my computer mic, it's the voice when it's recorded is very bad. But I think something happened to this one is because maybe the charge problem.
Okay, that sounds better.
Let's see. Let's see. If it's not good, then I have to use the computer mic, and then for that,
honestly,
yeah, the voice quality gonna be bad for those that do nothing. All right, so let's see if I can find anything else. Okay. So all of you have same issue with my mic? Brandon,
sounds
do
way
you
better.
have the same issue?
Yes,
Is it
Professor.
better? I didn't do anything.
We can hear you good now.
Is it good? Okay, probably it was misplaced. That's great. Okay, where we were? Oh, we were in the place that we wanted to produce the object file from the C file, right? So we said that if we say, do you guys can see my Linux what's called display?
Yes.
Okay, great. So if you use gcc test.c, right? If you say int there, it's not good. Why? Because this test.c, it has a function in it, and there's a factorial is missing, right? And you cannot basically compile to get the binary file or executable. So what you need to do, you need to create object file for your test.c and object file for your factorial function, and then you link them together with the libraries, the other libraries, and finally get the binary file and run it. So how you produce the object file from your C file? Then the option is -c. When you say -c GCC is going to produce you an object file. So now if you list, you're gonna see test.o. This is my object file from test.c, okay? You do the same for factorial, and then you have your object file for that. If you say list, then, you say list, yeah, fact.o should be somewhere in here. Here, this is fact.o. Okay, what else you need to do? So after we create the object file, we need to link them together. So there are two ways to link the file to object file. It is explained in the lecture video. One is use the GCC to link it for you, and the other one is to use the libraries. Let me go back and share quickly what the libraries are. So I showed you the library, but you might have forget that. Let me share that again very quickly. So these are the libraries for you. This is a dynamic linker. It's basically going to be linking all those libraries. These are the C library that you are having. These are the C library you are having. These are the C library. And then you have your object file in front of these two. So why this form in this way? This is the way that it works. If you go anywhere else in company that are working on these kind of things, the arrangement of this library and the way you put your object file is important, and for this happen to be like this. So you copy this and put it in Linux environment. Hopefully it works, but if it's not working right, then we have an easier command that we basically can create the executable using GCC simply from this to file, and that command is given to you in the lecture document. Okay, let's now try to see whether this is working for my case. Now again, we go back to our documents in Linux, and then let's see. Go down, down, down. Okay. So here are the two files that we create the object file, and now we want to link it.
So we're still on the Word document.
Oh, you're on the Word document? Okay. You haven't missed anything, just created the object file in there, and I just show the same document in Linux. So this is the same document, but because we want to make the copying easier, just use this. So you guys can see it now?
Yes, we can.
Yes.
Good, good, good. Perfect. So let's copy this and paste this. So we say Q to get out of there, and then we simply say paste. Okay, it is complaining. Why? Because when I paste it, then the things that I'm running is going to be run one by one. So one thing you need to do is to type those manually, probably, since it is kind of sees each of those lines as a separate command. So one thing you need to do, you just need to get in there and start typing that from the document. Or one thing else that you can do is just copy one by line. Probably that is going to work. Let's see if we can copy one line. And because that's too much work if you want to stay there and copy that line command, right? So first we copy LD. So if your screen is big, then you can open that in a separate Linux window. And so you do this, but remember that these two dash should be like this. There shouldn't be any space. Let's do something. Let's do something. Okay, let's vim the document. Probably that's the issue that I have in here, since the dash I purposely create two space for them, because in Word document, when I put one space in dash, sometimes the student only see one dash, and then the command gonna be problem. So I create space in between them so you guys can visually see that, okay, there are two dash, there's not one dash. And when I will convert docx into PDF, if there are one space in between them, PDF unfortunately connect them together and shows it as one dash. That's the reason I put two dash, so that PDF does not connect them and you guys do not see the issue this way. But since right now Linux see two space, maybe that's the reason it's complaining. Let's take a look at the document. So this is the command, the link command that you guys have. And as you can see, there are two spaces in here. We make it one space. Yeah. And then we save it and we get out of there. Let's see. Okay, we create two commands so that I can have one open in there. Module. I just want to cat it. Let's see. Let's this time we copy the command and try to paste it. If that again complain about that, then we probably need to do it line by line. We go back to the previous screen, clear everything, and try to paste it over here. Yeah, so we probably need to write it one by one. So do this. Just take a look at this and, you know, write all these library files. So when you put the linker in here, right, the other things you need to do, you put this in front of it, and then this in front of it. You don't need to go to the next line. Just put everything on one line and then enter, okay? All right. Yes, Daddy. Okay. Okay, let's exit. So is it any easier way to create object file create the executable from my object file? I have this object file, test.o and fact.o. Probably, maybe. So let's use the GCC command, test.o, and then fact.o. Yeah, this makes our work a lot easier, right? Now we have a.out. So you guys try that, the first technique. You see that it's a bit of a hassle. You have to type all these things, but GCC do good work of, you know, producing the object file for us automatically. And this is one of the things that I explained in the lab document. Now I have the a.out, which is my binary file, my executable. Let's run it. You see if everything is fine. So as you can see, it prints out x factor equal to 24. Good. Let's go back again to the document. Where is my document? All right. So here's the document. So we tried this one. It was not very easy. And then we asked, okay, if you have received an error, is there any other command line that you can use without directly calling x86 library files? Yes, there is. You can use GCC. And then you answer this question under activity 3.3. Okay, what else you are asking to do? Okay, all right, this is interesting. So this time it says, the other time that you generate those files was for 64-bit machine, but this time you have this file and your client says that I don't have a fancy 64-bit machine, so I have a chain of factory throughout the world, and this factory has been running for 50 years, and I don't want to spend any money to upgrade my machine. And all those are running on 32-bit machine. And I wanted you to run this service for me. And you say, that's no problem, I can do that. I can, you know, write some new automation algorithm for you in assembly and then run it on your 32-bit machine. So the way that I'm gonna be running it this time to get the object file, I put -m32 to say the compiler, this compiler is for 32-bit machine. Yeah, so I write my C file. Right now I said assembly file. It's not assembly file for this question, but again, that you can basically produce 32-bit object file for your assembly as well. Okay, off tangent a bit. So go back to our test c@.factc. So using these two commands, basically you just type it in there. And this time the object file that's going to produce for you is for 32-bit machine. Again, you use this line command this time. These are library for 32-bit machine. Those library up there were for 64-bit machine. So these are for 32-bit machine, and you should be able to run it. So this time we will put the option -m the 386. And then you have dash space dash dynamic linker. So this space between these two should be 1. You can see if I put 1, it sees as 1 dash. So I put a space, not to be mistaken. There are 2 dash in here. Dynamic linker at this one. Try this one, and you should be able to get the object file and run it. But if you are not able to do that, then you can use GCC. This time, what do you do? What's the difference between this producing object file this time and with the previous question? You have -M32. You say that, okay, I want an executable that run on 32-bit machine. Why? Because my client is asking for it. If I produce 64-bit machine, it doesn't work for him. He won't pay. He will not be paying for my service because basically my code is not going to work for him. That's the reason. So I need to use this switch. Okay, use this switch, and then there is the binary file. You give it to the customer. Customer is happy. You pay you, and you go back home. Okay, activity 3.4. Now I want to stop here and ask you guys if you have any question before going to activity 3.4. All right, let's see. So if you have any question, please put it on chat or speak out. All right. So I'm assuming everyone is good and ready to go for next activity. You are now becoming an expert in assembly and C and all this. I'm very happy for it. Okay, this time you're going to be linking C and assembly files. So one might ask, did you, professor, teach us this before? The answer is yes, it is in your module 3 video. Every single step has been shown using a graph to make it easier for you to understand what the hell is going on. So we can see all of this in that lecture. The slides are there, but please, I'm asking you, the slides are not for understanding the topic. The slides are there just for you as a way to guide you through the process if you have watched the video. If you have not watched the video, you won't be able to understand the slide. The slides are not for teaching the topic for you. The slides are there just to summarize what is going on for this topic. Watch the video and read the text file, the textbook, sorry. What section was it? 1.4, I think. It's given in module 3 overview. It tells you what to read. Section 1.4. Please do that. So you have some macros in there. What are the macros? We talked about the macro and what are the macro and why they are useful. They're useful because since you have just started assembly programming, for you guys, if you want to see some output and read something from the input, if you want to do that, it's going to be a hassle using assembly language, as we explained in the first strategy for Hello World program. So we use this macro to give us some way of debugging. So you can basically read from the keyboard, you can print out message from your assembly easily using this macro. You can see the content of the register using dump rich command from this macro. These are very useful. And then, so you can do tons of things. That's the reason we are here at the beginning saying that, okay, how to mix C and assembly file. This C file that is written on those header files are enabling you to debug your assembly code. Since this is very troublesome to do the debugging using GDB because you are all kind of starting your career in computer science and you don't have any idea about that, this is tough. So these macro are enabling you to basically debug your program and write assembly program in easier way. Okay, please, I'm asking you read the textbook, watch the video. Otherwise, it's gonna be struggling. This lab is the base for all the course material we are having. We are gonna be using this SQL file throughout the course, everywhere. If you don't understand this lab, then you're gonna be in trouble. Please, please, please read this material. I'm begging you do this. Otherwise, you're gonna be struggling. And it's like, why am I struggling? Because you don't watch the video, don't read the board. Basically, there's nothing. If you read this one, it's gonna doing these steps and process is gonna be very fun, and it's very fun. Okay, going back to activity 3.4. Activity 3.4 says exactly what we have been doing in lecture 3, and you are kind of reproducing those steps in this activity 3.4. It's not something that, okay, it's very new, it's very challenging, I can't do that, it's like impossible. No, we are just reproducing those steps in this lab for you to make your way easier for coming lectures. So basically, the students are supposed to reproduce this after watching the lab, watching the video, but maybe some students are busy doing a lot of, they have outside employment or they're full-time worker. So by asking this, in the lab, you're kind of helping them to follow the lecture material. Okay, this is the ASM_main, where you basically call your ASM function. That's in driver.c. If you take a look at driver.c, you're going to be seeing the same thing. Function asm.main. Okay, driver.c, you can create the object file for it using this command. Easy, again, that's for the 32-bit machine. My program.asm contain asm main label, meaning that in the main C program, I call this function, and then I define this function where in my assembly. So global ASM_main, ASM main, enter 0, push A. You don't need to know these two, enter 0, 0 and push A. We'll study this syntax at the end of the course, okay? Don't worry about these two syntaxes now. Don't worry about this. Can you guys see my lab document now?
Yes.
Enrique? Okay, so all right.
Yeah.
I thought that you're still on the Linux display. Okay, so don't worry about these two, and don't worry about these two commands. So one thing you need to do, just your code goes in between in here, whatever you do, okay? So basically in this simple assembly codes, we say, okay, put 100 in register EAX and put number 20 in register EDX. And what you need to do, you subtract EAX from EDX, means you subtract 100 from 20, and basically the result go into register EAX. And then what you need to do, you call print integer. Basically, subtract two number, then you call this function. What this function does, this function is going to print anything that is in register EAX. And now number 80 is at register EAX. So basically, it's going to print out that value for you. And this one is print NL. It's going to send the printer to the next, the cursor to the next line. And dump register is going to basically print out the value of all registers on the screen for you to see. And what is this 1 here? What the heck is this? This is only a label. So when we print out the content of the register, it's going to be printed out on the screen under label 111. Can I choose another label? Yes, you can choose another label like the 1. You can say dump register 1. So why this label is required? The reason is that you may want to print out the content of your register at multiple points in your assembly files for debugging, right? So you are at function A somewhere, you're gonna print out, then you come back at function B, or you're at line 10, you're gonna print out the content of the register. And at some point you decide that you wanna dump the register value at line number 100. Therefore, you give it a label so that you know. For example, line 15, you print out, you give a label 15. For line 100, you give the label of 100 for your dump register so that you know where you are dumping the value of the hardware register. So this is the way. So these are the macro that I'm talking about. These are the macro that make your life a lot easy for debugging, to seeing the content of your register, to see what's going on in the hardware now. So these are the things that you cannot do if you do the pure assembly at the beginning. At the beginning, you are not able to do that. Why? Because you just started. You can't use the fancy command to print out. It's going to be very complicated for you. If you don't believe me, go search internet, see how other people are teaching this course and how do they debug it. Type debugging assembly x86 architecture. See what you get and basically go search for a month or a year and see how much material you can get on this topic. Not so much material, not very good one are out there, I can promise you that. You cannot find a very good lecture on assembly out there. This is a difficult course. Not easy to teach. Different people take different approaches. Some people teach virtual machine, which is useless. Why? Because when you go to industry, they don't tell you, okay, can you write a program for a virtual machine? There's no hardware. So they ask you, okay, write the code for these machines, like either it's ARM processor or it is x86 architecture processor. So for that reason, we are teaching a real machine for you, real things that when you go out, you can use it. You will get experience in Linux. Why? Because when you want to write assembly, it's mostly in Linux. You write device driver. You want to do system programming. All this happen in Linux, not in Windows. You want to write an operating system. You do it in Windows? No, 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 no. You do it in Linux. You do all these things in Linux. That's the reason we have to learn the proper environment. If you're gonna be using like this on Windows machine, yeah, basically you're wasting 1 semester of your life on this and you don't get anything out of it. That's a takeout. Okay. So these are the things. So this is the code basically to subtract two number and see the content of the register after that. So this is the code. This is your main thing, and that's the main thing you need to do. This myprogram.asm is the program that you normally is a file that normally you code in it. The structure is like this. At the end of this code, you will be able to write your own C macro and combine it. You will be able to run to write your printf, printl, dump register, everything at the end of this course, you will be mastering it. If you follow the instruction and if you work and spend 20 hours a week on this course. If you spend 1 hour a week, then you're gonna be in trouble. You're gonna have a lot of challenges. You're gonna just bang your head to the wall if you spend 1 or 2 hours or 5 or 10 hours. You have to spend 20 hours at least. At least. This is a takeaway. Don't put like 4 hours and say, oh, I'm gonna be good, I'm very smart. Even if you are smart, it's not Einstein, right? You need to spend and work on program by your own. Okay, so you have to spend time on it to get master in this course. Okay, let's see. Now we write our program in here. So the other files in here, do we need to do anything with them to enable this macro? No. So let's take a look at those files. What are those files in there, right? Let's go back to Linux and see this. Let's stop share. And now let's share Linux. Okay. You guys can hear me well or something happening?
We can hear you, Professor.
Good. Okay, Linux, please don't disappoint me. All right, now we're here. You're talking now, okay? So what are the other files? So we talked about driver.c, just like few lines of code. We saw that, right? A few lines. See here. is basically a C file main, and we only call this function. Where is this function? We said that for this given program for you, now it's in my program.asm. Here you can see asm underscore main. So we said that don't worry about these two lines. Don't worry about these two lines, but you need to know exactly what is happening in here. What is happening here? Nothing. 100 goes to EAX, 20 goes to EBX. You subtract them. Result goes to EAX. Then you print the content of EAX using what? Using this macro. This macro comes from where? From the library files in this directory. Where are the library files? Library file. CDECL, SM underscore IO, SM underscore IO, sorry, this one. So these are basically your library file. Do you need to do anything with them? No, they're good. You don't need water. So you just need this file to write your code. This file is your driver.c. This is your library. You don't need anything to do with that. This is your library. You don't need to do anything with that. This is your library. You don't need to do anything with that. Even driver.c, you don't need to do anything with the content of this file. You just, when you were just want to create your binary file, you have to create the object file from this file and link them together to get the binary file. Okay, this is my prog. So we said what the content of my prog is. Now we go back again to the document. Here, okay, we talked about that. Now we say for those file, you need to create object file. To create object file for myprog.sm, you use this NASM command. Then link the object file myprog.o sm.o driver.o. You basically obtain this file, and now you obtain this file where? Here, for example. You obtain driver.o from this command, and also for your sm.io, you need to put like NASM command. I guess we haven't put that in here. Basically, you need to create NASM underscore io dot o using similar command in here. So once you create that, then this is a time to link them together. You link them together, and then you get the binary file. How do you link them? You can use this simple GCC command as a linker. You can use that long command, that long libraries, but since this makes our job a lot easier, we use this. Then we print ./a.out. Basically, we run it, and then we see the result on the screen. So when you basically produce your binary file, the system is going to produce a file name called a.out. But can you do something that you can specify your own output's binary file name? Yes, why not? Linux make that for you very easy. So once you want to do that, you just put a option called -o. -o, the file that comes after that's going to be your output file. Now you run this one, your binary file is going to be named myprog. And then you run it. And once you run it, what do you get? You get the result of your subtraction as well as the content of your register. So below is the list of syntax you need to run for this program. So we set step by step in this lab how do you create those object files and you run your program. Now we collect all them together in here. So we said that how you produce sm_io.o using this, how you produce driver.o using this, how do you produce myprog.o using this, how do you link them together using this, and what is my output file name? Is this my program? And how do I run it? ./myprog. You have to be the same in the same directory if you want to run the command. If you move into different directory, then the system tells you uh-oh, I can't find my prog. Where is it? Then you have to tell them where it is. Now we're gonna say, oh God, there's so much syntax in there. I'm gonna die after this lab. And if I wanna run all these over and over again for each, program that I'm coding, then I'm literally gonna die. So I'm gonna drop the course. So I'm saying that don't drop the course, you're gonna be fine. So we can use some other Linux tools to make this process automated for you. How? Easy. How? Just easy. You create a file called run.sh. How do you create that file? You say vim run.sh, and Vim create that file for you. Now you go into that file. What do? You just copy this syntax in the shell file. In the shell file. And then how do you run that? I don't know, Professor. I haven't written any shell code before. I just, started my computer science major here at CSCCI. I don't know how to do it. I'm just gonna quit. Don't quit. Can run it using this syntax: sudo run.sh myproc. Or if the file, you have given a permission to everyone to be able to execute the file, the executable permission 777, for example, to everyone can in the world can run this shell file for you on your computer, then you don't need to put the sudo in the beginning. You just say run.sh, my prog, is the name of the, basically that's the input argument that this shell file will get. So this is a shell file. The shell file is going to create the object file for this as like that. Gonna produce the shell, object file for driver as like this. And then this one, myprog.asm. So any program that you write, you may give it a different name, right? So this happened for this specific program, the name is going to be myprog, right? So what if you give it to program another name? Go give it like name like file 1 or your file 2 or sorting, for example, or printing or some other names that you like, right? So if you give it a different name, that's going to be fine. That name is going to be the argument for your shell script. Basically, when you run the shell script here, you say run.sh, the name of the file that you would that you have given to your assembly file. In this program, the name of the assembly file is myprog, but somewhere along the way in this course, you may choose different name. Don't worry, that's going to be fine. So you give the name to the shell file, and shell file is going to take that name, and shell file understand that argument as $1. So whatever name that you give that, the shell is going to be replacing $1 with that given name. In here, when you say myprog, shell is going to put myprog instead of $1 and then produce the object file for it. That's exactly fine. So once it's done that, then going to be producing object file for the $1.sm, in this case, myprog.sm. Then it's going to link that and create a 32-bit executable for us, right? And then you see that $1 again is there. So $1 is going to be the name of the output for this executable -$1. So going to be again having a file with myprog name. And then you have $1.o. This is the file that produced as a result of this syntax. Okay. And then at the end, the shell is going to run your binary $/$1. What is $1? myprog. It's basically Linux get an argument. That argument happened to be the name of your file. As simple as this. Okay, so the conclusion is that all these commands for running the mix of C and assembly file can be put in one shell file, and that shell file is going to run that for you and make your job easy. Just one line of command is enough to run it. Now let me go back to I don't know, you guys see which screen? Let me stop sharing that. Let me go and share Linux. And let's see, we have one chat. Okay, good. Now we are here at Linux. Please let me in. COMP-162, that's the password that you guys have also. Let's clear this thing. Okay, now we are here, right? We said that there is a run.sh file. Also, is it here or not here? Let's see, we put it in here, I guess, right? So you can see run.sh is in here, it's written for you, but you need to know what's going on in this file. So these are the explanations that I've given to clarify this issue. Hopefully this is recording, so you can watch the video over and over to understand it. So now we said that if we use basically the run command, right? Run sh myprog. Let's check the name. So we don't put a .asm, okay? Remember that. If you put that, you're gonna get error. If we have the proper permission for run, then we should be able to run it. But as you can see, we don't have proper permission. So if you say ls minus la, you will see that run sh is mostly only readable. You don't have executable access to the file, right? So one command that lets you to change the mode of that, like it's change mode 77. So I give it all the permission it requires. And like very, so now if you list again and check the permission status of run.sh, you see that I gave them all the permission that is required. Read, write, executable for the user, read, write, executable for the group, read, write, executable for the whole world. And that's not good. It's, in terms of security, it's the bad practice to give permission to the file so that everyone can execute. Don't do it when you go to work. Don't do this. Okay, run sh myprog. Let's run it this time. Okay, so we get our output. We got our output. The subtraction is AD. Register dump, we give the label. Do you guys remember the label 1111? So that's the label. And these are my registers. S at the end. Bunch of registers. Okay, so we have register EAX. Content is 50 hex. Remember that. 50 hex in decimal is AD. So, and that's the thing that we print out. Then we have register EBX 14. 14 is the hex. 14 is a hex, and if you find the decimal of it, this has to be 20. Let's go show you if it's 20. Is it 20? For example, 4. Can you guys see my internet screen?
Yes, sir.
0x14 to decimal, right? If you don't know how to convert it, but you should be able to convert that. So the content of your register EBX is 20. Why is 20? Okay, so the content of register is 20. Why? Because we put 20 in it. And so why we put 20 in it? So let's check. cat my prog. I say something and I write different thing. Cat my prog. Here it is, right? We put number 20 in register AX, number 100 in register AX. We subtract that too. Therefore, 100 minus 20 now is at EAX. So we saw that in here, right? And the rest of the register are having some random value. And the flag register is very important. Note that not all the registers having random value. This is the instruction pointer that point to the line that the program executes. So E6 is random, EDX is probably random. That one also is SI register. This might not be random toward the index register, segment register, index register. This might not be random. And this is a base pointer. This point to the, that's kind of the frame pointer for the stack. This might not be also random. This is a stack pointer. So, but the content of register ECX and EDX might be random. And whatever you print out in here is going to be show up in hex. So know that if you put some decimal value, you can check, all right? And that's pretty much it. So we print out the content. And one thing important is that the flag register we explained in the lecture note, that's a 16-bit register, right? So each bit tells you different information. And this number is hex. So when you convert this to binary, you're gonna get 16 bits. For example, you're gonna get 000, and then you're gonna get 0010. This is for these two. And then you're gonna get 000 for this, 040 for that. And then for this 6, it's basically 4 and 2. You get 0110. So you produce 16 bits, and then you can map it on the flag register to know what the content of each flag is. That's great. So guys, we somehow done with this lecture. So now this is the time for you guys, if you have any question,